Okay, so welcome everyone. So today I think we have a good timing. So um, I think we are fortunate enough to have our guest lecturer, Dr. Clarence Choi from University of Hong Kong. I think I would like to take opportunity to introduce you guys. He is the assistant professor from in civil engineering at the University of Hong Kong. And actually his research interest is really interesting. I can say he's working on the debit flow, which is I think the hot topic right now. And everyone, especially those engineers, also need to know what the mechanisms of the debit flow and what the solution that can mitigate that kind of debit flow as well. So his research expertise is focusing on that kind of debit flow. And he also working on the ground improvement as well. And you may see in the presentation, and he will show us about the research on debit flow and also the mitigation procedure as well. And his research is, of course, is very interesting, and he also got award in so many around the world. I can see from his profile, he got invited for Hutchison lecture and also Bright Spark Award, which is a quite a new award, but very important one as well. And then he also got for a Telford Premium Prize from ICE from UK as well. Currently, he also served as a chair of the Debit Flow and Steep Crack Hazard Committee of the Association of Geohazard Professionals. He also editorial panels of landslide and engineering geology. So I think his research have been proven that it's very important and should be very interesting. So that's why I can say we are very fortunate to having him as our guest lecturer today. So to save the time, I would like to pass this stage to Dr. Clarence. So please welcome Dr. Clarence. Thank you so much.
Yeah, thank you, Virun, for the very kind introduction. Virun was my colleague when we did our PhD together at HKUST with the same PhD supervisor. We studied together and had good and tough times together. And I think Virun is very humble as well. I was telling everyone that there are very few engineers like him and Om that can do well on the practical side and do well on the research side as well. So it's my great pleasure to be invited by Professor Kam Chung today to share some of our work in Hong Kong. Thank you for the awkward introduction as well, Virun. Yeah. So let me get started. I promised Virun that I would try to keep this slightly more instructional because the target audience is somehow mainly undergraduates. So I didn't want to go crazy with the graphs. So
thank you so much. Yeah.
So we'll keep it at that. Yeah.
I know you are more toward on that, but make it simple. It's much harder, I believe.
Yes. So I guess this is the title of my talk. We'll focus mainly on solutions against landslide hazards. We'll look at synthetic ones, man-made engineered ones, and also there seems to be a trend around the world recently to try to not use hard measures, but nature-based solutions as well. So I'll try to touch on that. At the bottom of my screen in the gray is not meant to hide them, but they are in essence my collaborators and some students that have worked on this project as well. I don't want to do this, but I have to as an ambassador of my university. I welcome you to visit us in Hong Kong anytime. We are a top 25 university in the world, research intensive. Engineering is one of the main faculties. We're a very international crowd. We welcome exchange students. We welcome students from all over the world. If you look at our demographics shown at the bottom of the slide, we try to diversify and internationalize. So that's one of our core objectives. We do have a significant postgraduate body. This is a testament of our strong research initiatives to try to push the forefront of knowledge. Our faculty is also very diverse, and this helps us to give the best insight to our students. So I welcome you to send me an email anytime if you want to visit. I'm happy to give you the grand tour of our campus. If you have any questions about admissions, I'm happy to direct you in the right direction as well. And I hope that perhaps in the future, Virun and I can perhaps set some exchange opportunities so we can get students going both ways. I wanted to draw some local relevance to Thailand because I guess my audience is from Thailand. It wasn't difficult to find a lot of cases when I typed in Google landslides in Thailand. There are, of course, a wide range of landslides. Some of them I found quite shocking. Some of them are very large scale. If they end up on David Petley's AGU landslide blog, as you see on the bottom left, it's pretty significant. I was reading on some of these cases. The debris flow at the bottom in Krabi province in 2011 affected 800,000 people. That's a very significant displacement, but astonishingly, there were only 13 fatalities, which is quite fortunate. You can also see the large boulders at the bottom of the screen there. This is very typical of a debris flow. We're able to transport very large particles, and these debris flows are complex from small particles that are clay size all the way to boulders that resemble cars or even homes. Now, landslides in Thailand is significant. I was trying to find some documented statistics, and I feel like this number is not representative. In excess of 100 million Thai baht, it must be substantially in excess of this value. And we're expecting that the frequency of landslide events should increase moving forward due to the advent of changing climate variables. The photograph at the bottom right here shows another type of landslide. It's not quite a debris flow, it's a landslip in, I'm going to pronounce this as Chiang Rai in 2018. And this case was a case of property damage. We didn't see any fatalities in this case, but why I wanted to show these two cases among the many in particular. Landslides are quite unique. Debris flows are only one type of landslide. We also have landslips, slopes instability, rockfall, and I'll try to make today's talk a bit more educational to showcase the different types of landslides, the landslide classification systems we use, and the potential solutions against them. So I hope this slide here, although it's quite simple, sets the scene for today's talk. And it's important to stress the potential impact and implications of our work as geotechnical engineers. Why should we spend more efforts on landslides? It seems like a topic very reminiscent of earthquakes. These are natural hazards that are ongoing, but why should we pay attention to them? Well, with the advent of climate change and with various scientific reports that justify we should expect heavy rainfall to change. We should expect extreme rainfall events. We should expect climate change to cause wetter climates globally. So if you take a look at this schematic from nature, you can see that there are regions around the world where there's a more likelihood of the change in probability of heavy rainfalls. And that's shown with the spectrum legend at the bottom. The darker the color, the more change that we expect. And you can see that in Asia, we have a substantial amount of increase in likelihood. So this is essentially the motivation behind my talk today. We should expect wetter climates, and we understand as geotechnical engineers that a wetter climate will cause increase in pore pressures and slopes and potentially decrease effective stress, leading to resistance, particularly shear resistance decrease, and potential increase in slope stability. So it's a chain of events happening, and that's how we justify our ongoing research efforts. I want to bring the presentation back to Hong Kong a little bit, because this is where I'm from. For those of you that have visited, this is a very interesting photograph of Hong Kong. You can see that we're very strapped for space. We cover an area of about 1,100 square kilometers. 60% of this landmass is on hilly terrain, and much less of that percentage of the 60 is usable for land. So we have two choices. We can either develop seawards by reclaiming land. That's where ground improvement comes in. Or we can try to encroach on the steep hillsides. Now, if you try to encroach on the steep hillsides, this raises a few potential challenges. Number one, we're worried about building very heavy structures on unstable slopes. Second, we're worried about natural terrain hazards. This includes rock falls and debris flows. Now, if you consider that Hong Kong is even more unique in that we have steep hillsides, we have thick layers of saprolitic soil that's highly weathered, and we also have torrential rainfalls during the wet season each year. Now, all of these factors make landslides very likely in Hong Kong. In fact, on average, we face about 300 landslides per year. We, of course, don't hear about these landslides because they are rather small events, but on average, about 300 landslips per year. So I hope this impresses upon you how the urban settings in Hong Kong are perhaps susceptible to landslide hazards because we're so close to the slopes. The next photograph I want to show you is quite interesting. If you look at this building here, you see that the top of the building is damaged. And this is quite weird. You might be thinking, how is this related to landslides? We expect landslides to basically slide on the surface of the earth and perhaps impact the bottom of the building. But why is this photograph showing damage at the top of the building? Well, Hong Kong has quite a legacy of landslide disasters. This is the famous 1970s Po Shan hillside failure, where a landslide essentially knocked a building over, and that building fell over and just grazed the top of this building here, essentially being one of the worst landslide cases documented in Hong Kong, resulting in substantial fatalities. So although Hong Kong seems like a very prosperous, safe, geotechnical marvel against landslides, this has not always been the case. We've had to learn from bad experiences, improve with geotechnology, and that's what has enabled us to become such a leader in the landslide discipline globally today. So I hope this helps to show that we've faced a lot of challenges in the past. I want to now talk about some educational components of the talk. You can see here that at the top of the slide, we tried to characterize our hillsides into two types. We have in the green, natural hillsides, and in the red, man-made slope features. So what are these? Well, let's talk about natural hillsides. Natural hillsides at the top here are generally hillsides that have not been affected or disturbed by anthropogenic or human activities. Man-made slopes, on the other hand, have been engineered. On this particular diagram, you can see that there's a dotted line here that shows the original topography. And what we did to rapidly develop on the hillsides of Hong Kong is to do a cut and fill slope. So what we did was we essentially cut this portion of the slope in the middle, and we took that material and filled it at the downstream end. So we call this cut slope and fill slope. The bottom half of the cut and fill slope are evidently man-made features that have been engineered. Likewise, we also refer to retaining walls, retaining slopes here as a man-made feature, and anything else above, we call it natural hillsides. The focus of this talk today is mainly on landslides associated with natural hillsides. So what are these? These are exactly what you see here. We can have boulders and rocks falling down slope. We can have debris flows, which are mixtures of water and soil surging downslope, picking up these boulders, and impacting various infrastructure. So I want to stress and frame the talk today to mainly natural hillsides shown at the top of the slope. And I'll place less emphasis on man-made slope features. And I hope that helps you frame the presentation. To further elaborate on the instructional components of my talk, quite commonly, we get quite confused with landslides. What is a landslide? Is a debris flow a landslide? Is a rock fall a landslide? Is a slip of a slope a landslide? Well, you're right. These are all landslides. Even avalanches comprising snow can be a landslide, right? Any mass movement of earth material we refer to as landslide. And debris flow is just one type of landslide. So it's important to have internationally recognized classification systems for us to talk to each other as engineers. It would be quite difficult to explain to Virun, for example, if I want to say this landslide looks like this, but it may not be very clear to him what I'm talking about. So fortunately for us, Varnes, Cruden and Varnes in 1978 and 1996 published a systematic landslide classification system. My focus today will be on two types of landslides, debris flows and rockfall. Now, what did Cruden and Varnes do? Well, they described landslides systematically using two main categories. Number one, what is the material type? Number two, what is the movement type? So at the top of the slide here, we can see the material type can consist of rock, soil, earth, mud, and debris. As geotechnical engineers, we may not be so confident what earth and mud really means, let alone debris. So bear in mind that this system, although we try to use it geotechnically, has also been influenced by geological engineers. So I'm not going to get into details today, but if you read up on these documents, there are very systematic classifications on what earth and mud is, pertaining to the liquid limit and the plastic limit of the soil. On the right side of the slide, to describe a landslide, we also try to use the prevailing movement. We can have fall, topples, slide, spread, and flow. If we had a rock perched on a slope and it just fell from the top of a hillside, we call it rockfall. And at the bottom of the slide is the table for the Varnes classification system. There's no need to go into detail here, but it's to show that Varnes and Cruden have essentially broken down complex landslide motions into 29 classes. The late Ulrich Hunger later revised the system, and now there are 32 classes of landslide. So today, we will only focus on rockfall and debris flow. And I hope that impresses upon you that this research only tackles a very small scope of landslide hazards. We're not trying to solve all problems because the solutions that I propose cannot solve all the problems. To further break down the types of movements, the main focus we'll be looking at today is the bottom of the slide here pertaining to flows. If you're curious as to what fall, topple, slide, and spreading looks like, they're shown at the top of the slide, and there are some definitions there, but it's strictly unnecessary for today's talk. Of course, you can find Professor Ulrich Hunger's 2014 manuscript in Landslides to understand the type of movements more. So I'll leave that as it is. Why do we want to talk about debris flows and rockfalls today? Well, I feel like these are perhaps the most destructive. How do we characterize the destructive significance of a landslide? Well, thankfully, Varnes in 1996 further extended the landslide classification system to include a velocity class, essentially from 1 to 7. The faster the landslide, the higher the velocity class. And we can expect that the faster a landslide is, whether it's a rock or debris, the less time you have to evacuate. There are, of course, slow-moving landslides as well. And if you're focusing on the hot topics around the world, we're interested in how climate change and changing climate variables, cyclic climate loading is affecting the movement of these very slow-moving landslides. These slow-moving landslides have already failed, and they're perhaps creeping just millimeters per year. But the scary thing is, we don't really know when these landslides will suddenly accelerate and cause catastrophic failure. So just to give you a bit more background, today we'll focus on only the extremely rapid landslide classes near the top. We're talking about movements in excess of meters per second. Debris flow and rock fall can travel in excess of 10 meters per second, just for your reference. So what is a debris flow? We've been talking about debris flows for a while. So here is a recent event in Japan. I think this was in 2021. You've probably seen this on YouTube and various social media. Yeah. So we can see that a debris flow is very mobile. It's almost fluid-like. It can carry all sorts of debris along the path, including buildings, vegetation, and there's really not much time to escape and evacuate because of the speed. Also look at the impact force resulting from the debris flow. It entirely destroyed the house along its flow path, took out the power lines, and it can even carry cars. So this is what a debris flow is like. So that's as much background as I want to give pertaining to characterizing the type of landslide for today's lecture. The next part of my talk will basically focus on the types of mitigation measures, hard measures, to protect the general public and infrastructure against these debris flows. These solutions will be broken down into 3 sections. The first section, I'll talk about engineering solutions. This is practical. There's not going to be a lot of fancy research tools being used. We tend to go for large scale or field scale solutions. And we try to propose solutions that can be used by engineers. We're not going to propose constitutive models that require 14 input parameters or only 3 PhD researchers know how to run the model, right? We're talking about very simple to use engineering equations and solutions that are always on the conservative side. So that's the first part. The second part, I would still call this ivory tower research, nature-based solutions. It sounds very attractive, doesn't it? We can use nature to help us protect the general public from landslides. But this is just the beginning of this research. To actually implement nature-based solutions, that will require some time, and it'll require experienced engineers to be able to, I'm just going to mute this person. Oh, they muted themselves. Okay. We need engineers to be able to draw design guidelines before we can use nature-based solutions. But I'll talk about our ongoing research on nature-based solutions. Lastly, I want to talk about defining new frontiers, because the bulk of the audience is, well, you are undergraduates. So I want to impress upon you some new challenges that we face as a society. And hopefully I want to encourage you to pursue a research career in geotechnical engineering. So let's start off with engineering solutions. There's a bit of vibration upstairs. I'm not sure what they're drilling, but I hope this doesn't affect you too much. I'm sorry about that. Yeah. So before we get more in depth into the topic, when I showed you the Japanese debris flow earlier at the event, there wasn't a lot of large boulders. Now, I want to show you a case where these debris flows pick up large boulders. So this is a debris flow in Ilgraben catchment in Switzerland. This is a very active debris flow site. And look at some of these boulders at the front. These are the size of small homes or even cars, right? So I just want to impress upon you that debris flows often carry very large boulders at the front of a debris flow. And if we are to mitigate this hazardous phenomena, we have to be able to rest these large boulders and also the slurry of the finer soil and the water in the tail. Now, how do we do that? Well, here's the existing art in Hong Kong. I think Virun and Om have probably traveled on this road quite a bit. This is the Seoul Highway to the International Airport in Hong Kong at the bottom of the slide. You can see the good old double-decker bus there in the yellow in the middle. So if you want to know about the scale of these rigid barriers, just take that double-decker bus and put it beside the rigid barrier. And I hope you can see how massive these rigid barriers are. It's because these barriers are so massive, we cannot place them further upstream on the slope because they will impose such a large surcharge on the slope and cause slope instability. Other issues with rigid barriers, when they become filled with debris flow, you need access to be able to clean out the barrier. Note that a barrier is very different than a dam. In Europe, we use a lot of mitigation measures called dams. Dams are meant to impound long-term loading, long-term soil loading, or they're meant to be filled. Barriers, on the other hand, are just meant to block something and you have to clean them out afterwards. They're not meant to impound long-term loading. So this barrier is placed at the bottom of the hillside because we can get construction vehicles in there to empty these barriers after they've been filled. But another issue we face is if we put one of these barriers at the bottom of a slope, what does that mean? Well, it's counterintuitive because we're letting the debris flows accelerate downslope, reach larger velocities. We're also letting them entrain more bed material to grow in size. And that means we need very large barriers at the base of the slope. So it's not quite smart to use these rigid barriers now, is it? So this is the existing art, and we tend to use these massive monolithic reinforced concrete structures because they're easier to construct. We tend to think that the impact loads are more predictable on a rigid surface. So this is one of the existing arts we use, not just in Hong Kong, but globally as well. Now, there's an emerging art. These are called flexible barriers. Flexible barriers were not originally meant to arrest debris flows. We used them for rockfall and we used them for snow avalanches. It's only that we were so lucky that some of these barriers in Europe were impacted by debris flow, and it turns out it works quite nicely. So if you look at this photograph here, you might be wondering, where are these flexible barriers? Well, they're somewhere along the middle of the slope here. There's a long span of them in the middle. And if we blow it up, that's how it looks like. So what are the advantages of flexible barrier? You can see they blend in well with the natural terrain, right? It blends in well with the natural environment. They're much smaller in scale. They're not visually intrusive. You can install them further upslope so that the debris or the rock don't pick up velocity and momentum, so we don't need to have such massive structures. These are also cheaper to construct, but of course, everything has limitations. You can't have such large volumes because these nets are limited in size. There are weak points. The posts of these barriers, if they get hit by a boulder, might incapacitate it. Also, it's made of steel, and in Hong Kong, the environment is extremely corrosive, and we're starting to see long-term problems with serviceability of these flexible barriers. Notwithstanding, the concept of a flexible barrier is, you can imagine it's like a net that enables deformation. And we know that anything that enables deformation can help to absorb impact energy. So these are the main types of mitigation measures that I'll talk about for the debris flow component. How do we predict the load on these structures? Well, let's use engineering approaches. Let's not talk about academic approaches with fancy equations with 32 input parameters to match the impact load. This is what we use in design guidelines globally. It's quite simple, based on the conservation of momentum. If we take the equation at the top of the slide and we further dissect it down based on the conservation momentum, we can break it down in the second equation in the middle of the slide there. And we can very quickly understand why we benefit from a flexible barrier. It's because of the relative movement between the flow and the barrier. And this is very much reminiscent of a boxer, right? You see the boxer on the left there. If he moves towards the punch, it's going to hurt him more than if he can move backwards while he's being punched. It's more or less the same concept, right? We want relative movement between the flow, impacting the barrier, and deformation with the barrier. So this is one mechanism. Of course, a debris flow flexible barrier has other mechanisms, such as it's a little pervious, so we can let a bit of momentum on the discharge pass through the flow, pass through the net, so the net doesn't have to absorb as much impact energy. Also, when we arrest the flow, we've learned through research that granular debris flow is very frictional. The moment you even shear the flow, you can mobilize a lot of the frictional resistance in the flow, and the flow will rapidly attenuate. And so there are lots of mechanisms we can learn just by looking at a simple conservation of momentum. At the top of the slide is, in essence, what we use in design practice to predict the dynamic impact force. F is the force, alpha is some dynamic pressure coefficient, rho is the bulk density of the debris flow, v is some impact velocity, h is the flow depth, w is the flow width. Now, you might be thinking this variable in the red here, dynamic pressure coefficient, it can be anything, right? Well, yes and no. If you look at it from a theoretical point of view, based on the expanded relative movement momentum equation at the bottom, if we have an alpha of 1, this essentially means whatever you impact at the barrier is arrested immediately, it's attenuated, and comes to rest. V final is 0. Now, if you pick an alpha of 2, this is perhaps the extreme case where something hits the barrier and then reflects in the opposite direction at the same velocity. That would augment the impact force by 2 times. So there is some theoretical relevance in the hydrodynamic force. The second type of force we consider is the retained static load. And let me showcase you this static force with some sort of experimental video. So in this video, some debris mixture will come from the bottom to the top of the slide, and some of it will hit this plate here, some of it will pass through downstream. So why do I want to show this video? Well, I want to show that even for a dynamic scenario, you can see on the left side, there's retained static loading, and there must be some static contribution during even a debris flow impact event. So there are design guidelines that cater for static loading. We can use earth pressure coefficients. 1/2 rho GH squared will give us a nice static load. So I think that's easy enough for us to understand as geotechnical engineers. So based on these simple concepts, we want to use something that engineers can relate to. So we can just combine the dynamic and static components to get the total impact force. Sounds easy, right? Well, yes and no. The static load can be made conservative if we assume the earth pressure or the pressure coefficient is 1. We know from geotechnical engineering that a pressure coefficient of 1 is basically treating this debris like water. There's no internal strength, right? That's easy to make conservative, but the dynamic load on the left is not so easy to predict. The theoretical values that I mentioned earlier of 1 and 2 for alpha is perhaps for an idealized incompressible fluid like water, but we can probably surmise that a complex mixture of soil and water is not like water at all mechanically. In fact, debris flows even have boulders. So what do we do? Well, let's remove the boulders from the equation first. We'll talk about it later because the boulders are just very difficult to assess. Let's talk about soil and water mixtures. So what happens when we have to deal with soil and water mixtures and assess the dynamic impact load? Well, if we dig up all the design guidelines from around the world, from Canada, mainland China, HKSAR, Italy, Japan, and Switzerland, we can see that all the dynamic pressure coefficients are mutually inconsistent. This essentially means we don't know what to use for the pressure coefficient. So we have to now rationalize this value by carrying out systematic research and changing independent variables and generating unique experimental evidence to study the effects of each variable. For example, particle size, volumetric content of solid relative to fluid, impact velocity, impact height, and also the competing effects between the dynamic and static load. So that's what we need to consider. And I can't share all the research findings in the talk today, but I can fast forward and show you the ultimate outcomes. So how do we study this problem? Well, I'm a physical modeler. Varun's also a physical modeler. We understand that physical modeling requires scaling considerations. If we don't have scaling, it really doesn't make us unique as physical modelers. Anyone can do our job and make a model. The key task with physical modeling is how do we link reduced scale model phenomenon and expand it back to full scale. That's how we draw implications in research. So the question at the top of the slide is, can we just carry out benchtop experiments? My answer to that is no, and I'll explain why. I'll try not to make it too complex. There are three core reasons. The first reason, if you look at the nice schematic on the left showing the gas, liquid, and solid behavior of dry granular flow. Dry granular flow is very interesting. It's a very complex phenomenon. In fact, it's mentioned to be one of the most complex scientific topics for research. That's why you see publications of dry granular flow in top journals such as Nature and Science, because it's so difficult to understand. Dry granular flow can behave either as a gas, a liquid, or a solid. It depends on how fast you shear it. What is the shear rate you apply, and also what is the overburden or confining pressure you apply to it. So based on this, we know that dry granular flow is stress and shear rate dependent. So automatically, we know that the scale of a model will affect the stress level. So benchtop experiments are likely to be not correcting correct stress state of the particular model. So that's the first problem. The second problem is, if we talk about biphasic mixtures, what I mean by biphasic are, let's say, sand and water mixtures. We know from basic consolidation theory, 1D consolidation theory perhaps, that the thicker your geological material, the longer it takes for the pore pressure to diffuse. So imagine that we have a debris flow that's 10-meter thick. The time scale to diffuse the pore pressure will be much longer than if we had a lab scale model that's only 1 centimeter thick. Why do we care about the pore pressure? Well, when we generate excess pore pressures in the debris flow by shearing it, we know that we generate sustained pore pressures that help make the flow liquefy and travel much further. Anything that can generate excess pore pressures will increase the mobility and the flowability of a debris flow. So imagine you have a very small debris flow that's only 1 centimeter thick. What you'll find happening is that the liquid will dissipate very quickly, and then the solid and the liquid phase will separate, and you'll have lots of suction in the sand, and you'll be unable to generate a flow that's coherent, where the solid and fluid phases are together. So that's the second main reason. The third main reason why we can't carry out benchtop experiments is just a proportional issue. Proportionality in terms of effects of viscous shearing to inertia. If you have a flow that is too shallow, the viscous effects of the fluid, when I talk about the fluid, it could mean the clay and water mixture, will overcome or overdominate, essentially, the inertial component of the flow. So it's just a scaling issue that we have to deal with. So these are the three core explanations on why we cannot just carry out small scale experiments. So where am I going with this? Well, I want to show that because we cannot carry out small scale experiments for debris flow, it simply will not work. We have to carry out field scale flows. And this is in collaboration with Professor Charles of HKUST, and we've developed a facility at the HKU Kadori Center. So let me just show a video. Let me show a video of this. So this is a facility that's about 28 meters in length. It can model 10 cubic meters of debris flow. There's a gate at the upstream end here that's controlled with a mechanical arm, and we store 10 cubic meters of debris behind it. And when the gates open, the debris will surge down the channel. Inside the channel is instrumented. So here we just use a concrete truck to funnel pre-made debris mixtures in. We can have UAVs to capture the displacements and velocity fields. We can see that this is the mechanical arm of the door opening. That's the debris moving downslope on top of instrumentation. This is the flexible barrier model with scaled deformation. This is another view of the same process. This is a side view looking at the deformation of the flexible barrier. Plan view. Some more fancy views of the UAV. And afterwards, we can study the retained profiles of these barriers. And this is, in essence, a large-scale facility that enables debris flow research. Now, along the channel bed of this facility, we've installed a lot of instrumentation. The reason is physical modeling is only as good as what you can measure. So we developed in-house debris flow cells to measure the pore pressures generated at the base, normal stress, shear stress, and by knowing the normal stress, we can deduce the bulk density of the flow if we place a laser sensor directly above it to get the flow depth. So here are just different views of the special instrumentation we developed in-house. We use triaxial load cells to minimize the number of cables that we need, and that's what we use. Now, the debris flow mixtures that we use in our experiments have been benchmarked against other reported findings for compositions of debris flow. We use this nice sand, gravel, clay, and silt triangular structure here to characterize our flows, and we are just somewhere here with this square and red X marker. So we try to have debris flow mixtures that are reminiscent of Asian debris flow mixtures. The volumetric solid content we use is 60%, which is in line with most debris flow mixtures globally. So now let me show you some typical test kinematics. As I mentioned, we carry out years of research, decades of research on debris flow impact to look at how different types of structures such as rigid barriers and flexible barriers would behave. So let's take a look at the rigid barrier on the left side. So nothing fancy here. We have about 2.5 cubic meters of debris flow impacting a rigid barrier that's heavily instrumented. We have load cells behind the rigid barrier, so we can measure the bulk density of the flow and the load, and back calculate some of the pressure coefficients. Likewise, on the right side, we have a 10 cubic meter debris flow impacting a flexible barrier, and it smothers the GoPro camera, and you can't see much after that. So these are just typical observed impact kinematics for different types of barriers using the large-scale facility. So let's fast forward from when we started this research to about 10 years down the road. Eventually, working with Professor Charlesman and his team, we developed a rationalized combination of static load, dynamic load, and proposed impact coefficients relative to existing design guidelines. So what were we able to achieve? Well, research is not very useful if you can't make an impact in practice. So we were able to work with industry to change recommended values in design practice. Now, this is the most important impact of any research. Can you change design practice? Can you get your research to be relevant in design guidelines? And we were able to contribute to rationalizing the reduction of the design capacities of rigid barriers by 40%. So the alpha values for rigid barriers used to be 2.5. After our research, we were able to tone this value down to about 1.5. And hopefully we can see the rationalization of flexible barrier alpha coefficients from a value of 2 to 1, representing a 50% reduction in design capacity. And any reduction in design capacity is pretty much saying that we're reducing cost. So we hope that we're no longer over-designing barriers because we don't understand the impact mechanisms. But now with the rationalized experimental evidence that we have using large-scale facilities, we can bound the impact pressures and propose optimized values, not just locally, but hopefully globally as well. So that's all I want to share pertaining to debris flow impact. Now, the next question that I raised throughout the presentation is, what about boulders? So we see a nice home here that essentially was destroyed when a boulder rolled down from the hillside just to the left and essentially demolished this home. So you see the two boulders on the right here. You can see two things. Well, boulders are extremely destructive. They're very large. They induce concentrated impact loads on structures. And often the boulders are the geomaterial that are incapacitating mitigation structures. So inevitably, we have to consider these boulders. So how do we do that? Well, lucky for us, in the Jiangjia ravine in Yunnan province, China, there were some field measurements. We see pressure on the y-axis and we see time on the x-axis of some sort. And what do we know from this? Well, we can see that there's two types of loads. There's the distributed loading from the soil water mixture. By soil, I'm not referring to anything boulder-esh, such as anything larger than 200 millimeters perhaps. And we also see concentrated loading from boulders. These are very short impulse loads that generate very high pressures on the load measuring device. So we can immediately see that, yes, great, the previous slides I show you can probably cater for the red line. But if we don't want our mitigation structures or barriers to fail, then we perhaps have to consider those spikes in the green dash box. So how do we design for the boulder impact force? Well, to be very frank, it's very difficult to estimate boulder impact force. I'll explain why. A boulder, when it touches the surface, let's say the surface doesn't deform much, is in essence a single point contact. Now, a point contact and an impact pressure applied to it can result in an infinitely high stress, if you think about it, in terms of force over area. So how do we propose any approach to rationalize the computation of the impact force? We would have to also consider maybe there's potential deformation at the surface of a hard inclusion impacting a deformable surface. So most design guidelines around the world adopt Hertzian contact mechanics. And the problem with Hertzian contact mechanics is we assume linear elastic behavior that's isotropic. We don't consider any frictional components. We assume that the contact radius is much smaller than the dimensions of the bodies involved. And that's how we can get some equation to predict the impact force. Now, based on the body of research we've done, we know that Hertzian contact mechanics, which is purely elastic in nature, substantially over-predicts the impact force by the boulders. You could say we are safe, but on the other hand, we might also have a lot of design problems because the impact forces we predict are not practical to mitigate against because they're too large. So through research, a lot of reports have proposed the use of a load reduction factor in the Hertzian equation. The equation you see on the left side of the slide is semi-empirical because in GEO, the Geotechnical Engineering Office Authority of Hong Kong, proposed a special form of this formula where they adopt Poisson ratios and elastic moduli specifically for granite boulders, which we see in Hong Kong, and reinforced concrete surfaces. So then you can get this simplified Hertz equation, and the load reduction factor can be anywhere from 0.1 to 0.5. And the reason we do this is we know that the forces calculate are overestimating impact forces. So we need to discount the forces for there to be any rational design. So this is the existing state of predicting the design boulder impact force. So we have some approach to predict the design impact force. We know it's over conservative, but what type of structures do we place to trap these boulders so that we can minimize the impact capacity on our barriers? What you see on this particular photograph here is a flexible barrier in the background. If you look very closely, and in front of the flexible barrier, we have what we call steel baffles. Look at the structure of these steel baffles. We have a concrete podium, and then we place essentially an I-beam. And we connect the I-beam to the concrete podium using bolts. Bear in mind that this design has not been evaluated or validated, right? We just place these prescriptively in front of a barrier. Conceptually, we understand if a boulder hits this baffle should survive, the I-beam should deform, it should take some energy out, and hopefully it doesn't impact the post of a flexible barrier or damage the concrete face of a reinforced concrete barrier. So conceptually, it's easy to understand why we place these steel baffles upslope. Now, I would consider boulder impact on a shallow footing with the I-beam an extreme soil structure interaction problem. Why is it extreme? Well, I talked about it already. We have a boulder with a point contact on a structure, which means that the stresses will be infinitely high. So the first step is to evaluate the design used in the field. And that's exactly what we did. So if you look at the drawings shown on the slide, this is exactly what we use in the field in this picture here. You can't see the foundation for obvious reasons, but in the field, we use anchors to tie down these baffles into the soil. So you have two views here. On the left here, you have a side view, and on the right here is a front view, and we use anchors to tie down and hopefully mobilize resistance as this baffle is impacted by a boulder. Now, we might be thinking, well, this is a very interesting problem as a geotechnical engineer. For me, it's interesting as a researcher because I have lots of questions that pop in my mind. What's the rate-dependent soil behavior that we should expect? Is it different than quasi-static loading in the soil for the steel dowels? Is there an inertial effect? Does it matter how heavy the baffle is relative to the boulder? How will this shallow footing behave? Is there going to be rocking behavior as in earthquake problems? Do we care about sliding? Can we mobilize passive resistance? Is there going to be compression waves from dynamic impact? How do we cater for this inside the constitutive models of the soil? Last but not least, we have localized and global deformation, potentially leading to plastic hinge formation from a structural point of view. So if you think about all these questions, it becomes a very complex problem. However, we decided to impact one of these structures in the field first, and let's see what happens. Well, if you're not sure what happened, let's take a look at the PhD student here. He's not very happy because we did not expect this to happen. We didn't expect there to be structural failure. This baffle configuration doesn't work at all. It's because the boulder is much heavier than the baffle and the footing. It doesn't even mobilize any resistance from the foundation. So we had to stop this research project in collaboration with industry, and we had to go back to the drawing board. So when we went back to the drawing board, we realized that there's no need for such a complex design. Why don't we revise our design to just a pit in the ground, one monolithic hollow section, and then we fill the hole with concrete. There's nothing fancy here. It's a very simple engineering solution back to basic principles of participating mass ratio. We just make this thing as heavy as possible so we can mobilize resistance from the soil. And let's see how it works. Well, works fine, works like a truck. No need to have such complex structural connections, no need for fancy ground anchors and tiebacks. And this works quite well for up to very high energy levels. What you see here is 50 kilojoules, and this was a joint project with Dr. Andy Suyuchun in Nanjing University, one of his sites. So he was able to help us with carrying out the experiments here. So this project just started and we just finished the test. We haven't had time to interpret the results. And as I mentioned, this can be a very complex soil structure interaction problem. But we can see furthermore that if we evaluate their measurements against the Hertzian impact equation, we're well below that. So we know that's a conservative upper bound. We can also carry out successive impacts on these particular baffle structures to see their maximum capacities. And eventually you can see that for various configurations, the loads will plateau. And the reason is we eventually form a plastic hinge in the steel structure and they can no longer bear any more load. And that's why after the third impact, all three of these lines plateau. Essentially, the y-axis is the impact force. I apologize for not talking about that. And the x-axis is the number of repeated impacts on a particular structure. So hopefully in a couple of months, when we improve our interpretation, we can share more unique findings with you. So the next question is, what's happening with this problem? Well, we haven't had time to think about it because we've had to initiate the next project. We want to combine several baffles with industry to create straining structures to catch these boulders using several steel members placed inside concrete footings. So we're having to now revisit our data and look at using large deformation, nonlinear, finite element model to capture the response of these straining structures so we can place these types of structures on the hillsides to rest boulders before they impact the flexible or rigid barriers, and this will save impact capacity and cost. So I want to just showcase this slide to show you that we're working on straining structures, but we've barely scratched the surface. We really believe that force-based approaches are not so reasonable. We should be looking at everything from energy-based approaches first. The reason force-based approaches are not reasonable, we've learned that it's very difficult to evaluate how reliable your forces are if you measure it using an accelerometer and just the mass of the boulder. We're also not sure how sensitive the constitutive behavior of the soil is. So is there any value in carrying out complex numerical modeling? So I've just thrown a bunch of questions out here, not to confuse you, but to show you that there's a lot of work to work on in this dynamic soil structure interaction realm of research. So that's all I want to talk about for engineering solutions. That's the practical part of the problem. Now let's look at the more research-oriented part. I call this the ivory tower research, which it's a joke, but hopefully one day we can rationalize nature-based solutions to use for landslide hazard mitigation. The main question I want to talk about is, do forests provide a natural barrier effect? If they do, should we consider forests when we carry out routine numerical modeling of how far a debris flow will travel? If you look at this particular photograph, you can probably see that trees grow as they wish. There's no fixed pattern. Trees essentially need some fixed distance so that they can get enough nutrients and survive compared to other tree stems, right? Virun would be an expert in telling us about this distance here, but I'm sure that there must be some distance and trees probably don't want to grow too close together. But in essence, I understand in forestry and agriculture that there are models to characterize the pattern of forests. Notwithstanding, there are other complexities with using forests as a natural barrier. For example, trees can uproot. If they're impacted by a very heavy force, they can either rotate over, detach from the ground, become part of the debris, or if a tree is very strong, nothing will happen to it. Another problem is there are such a wide range of geophysical flows. We talked about landslide classification very earlier on. There are different types of flow compositions. There are rock avalanches, debris flows, debris floods, hyperconcentrated floods, and even snow avalanches. Do we expect the dynamics to be similar among these different types of flows? This is quite an intimidating problem. There's so many variables involved. We haven't even considered the soil underneath? Can the debris flow pick up the soil underneath, entrain, reduce the stability of a tree? And how does this affect the overall problem? Well, Virun and I would know that our supervisor during our PhD always tried to quote this individual here, Albert Einstein, essentially saying everything should be made out as simple as possible, but not simpler. And that's in essence, the approach I want to take here. This is research work done by a PhD student in our research group. We know that existing field data is largely incomparable and incomplete. What do I mean by that is a forest in, let's say, Japan may not be comparable with a forest in Alaska or BC, British Columbia. So it's hard to generalize any conclusions because existing field data doesn't let us because it's so unique. And even if there is field data, often the field data reported is not very comprehensive. You don't have some researcher counting the number of trees that was uprooted, or essentially looking at which trees bent, where the location of the tree stems are, right? So field data only tells us that it appears that forests work sometimes. The next issue that I talked about is how do we capture the effects of uprooting? Well, fortunately for us, I will be working with, well, Varun and I have a nice friend called Anthony Leung. He's an expert in uprooting. We'll be working with him to model the uprooting component. The next issue that we talked about is trees grow as they wish. So what patterns of forest should we look at? Should we look at regular patterns first? What happens if we have irregular patterns? And as I mentioned, there's such a wide range of flow types with different types of flow dynamics. How do we generalize? On top of all that, I haven't even mentioned slope, the effects of flow velocity, thickness, density, whether you have single, biphasic boulders, different viscosity, tree diameter, and tree height. So if we follow the principle of Albert Einstein, we decided to just look at regular tree patterns first using dry granular flow. And then we will progressively expand our research to look at more complex patterns using dry granular flow and trees that can uproot. So let me share with you some of our preliminary findings from our research. Now, we always have to look at this problem from a simple point of view first. Dry granular flow impacting a cylinder is actually reminiscent of a problem we see in another realm of research. If you look at the photograph on the left of the slide, you see a jet essentially creating a supersonic boom, a cone, in the air. Now, let's change the reference here. So we can imagine that the jet is the obstacle, the tree stem, and the air that the jet's moving in is the dry granular flow. Now, what happens if we do that? Well, if we do that, we see that dry granular flow hitting an obstacle will also form cones. In fact, depending on whether the flow is steady state or transient state, the shape of the cone will differ. For steady state flow, we get quite a linear cone, as you can see in the middle. For transient state or unsteady flow, we see parabolic cones. We can also use the concept of supersonic flows to describe this problem. Why can we do that? Well, supersonic only means if the flow velocity is greater than the sonic speed in the medium. And the sonic speed in air is, yes, 340 meters per second. In water, about 1480 meters per second. But interestingly, in dry granular flows, the sonic speed is only less than 1 meters per second. That's why we can generate these cones. Why do I want to show this? It's because if you want to model flow-forest interaction, if we cannot even model the interaction between a flow and a single stem, we have no chance of modeling flow and multiple stems. So this is one aspect we looked at. I can't share too many results with you today, but we spent a substantial amount of time modeling the correct cone resulting from flow structure interaction at different speeds. Now, let's add the next level of complexity to this problem. What if we have stems adjacent to each other? Let's say we have dual stems or two stems in dry sand. Then what happens is we get these jets or the cones essentially interacting with each other. in between two stems, we see that the flow will actually accelerate because the momentum is concentrated between stems. And evidently, this is influenced by the spacing between the stems. If your stems are very wide apart, you're not going to have any near field effects. But if you place them very close together, you can see momentum concentration. And on the extreme end of the spectrum, if you have them touching each other, it's almost like a rigid barrier. So these are the effects we want to model. Now, we need to think about this for a second. These cones are very specific in shape in terms of angle, length scales, stand-up distance upstream. So how do we obtain stem scale measurements of flow density, depth, and velocity so that we have any chance of modeling for scale dynamics? Using conventional instrumentation and experimental means, there's no way for us to measure the shocks and interaction between shocks. So we need to use a new paradigm of methodology. Now, just like any other research, we often want to create a ground truth. So this is easy for us. We've created lots of physical models, and here we just create another one, a model for us with a regular pattern, so triangular array of aluminum cylinders that are more or less rigid. We can vary the spacing of the stems to model sparse forests and dense forests. And at the top of this model, we have a container to hold the dry ground material or debris flow that's wet and release it downslope. Now, if you look at the two GIFs at the bottom, you can probably see that how do we even use this data to calibrate a model? Because number one, it's dynamic. Number two, look at the number of shocks we have to capture. And these shocks are not the same. They diminish along the flow direction from left to right. We have to be able to capture the local changes in velocity, the local changes in flow depth, and look at the complex pattern of the dense forests. If you notice carefully, the flow front in the dense forest case is much faster in the middle than it is spreading towards the side. So how can we even track this dynamic process? If we use the camera mounted on top of this model shown here, we're capturing hundreds to thousands of frames per second. Surely we cannot ask our PhD student to annotate 1,000 frames per second. I think they would quit, right? So we need an approach to systematically define these flows. So we leverage machine vision, so a type of machine learning. In case you're not sure what it is, it happens to you when you're walking around at the airport. You're perhaps being tracked for your temperature, or you're being identified, right? So how do we use the same technology? Well, we use a fully convolutional neural network to trace and ask the computer to detect the edges of the flow. You might be thinking, why can't we just draw it? It's very difficult because there are shadows. It's difficult to identify what the flow is because the density of the sand is different. Near the edges of the flow, it's much thinner than in the body of the flow. Also, we have black lines, trees, and board and sand. A human being drawing the outline of this flow will draw something different for each time step. And if we have person A and person B compare the profiles that they draw, I'm sure that it'll be entirely different. So we rely on a machine vision program to annotate each photograph for us and to draw the outline of the flow. Why are we doing this? Well, we're essentially digitalizing our experiments. Otherwise, there's no way to compare their areas, velocities, displacement, and there's no way to prove that the numerical model that we use later is a high fidelity one. More often than not, we see a lot of research papers only show 1 or 2 frames, compare it with the physical phenomena at different times, and say, look, we've calibrated our model. But this is not a high fidelity model. You should be able to capture the kinematics for the entire flow process, right? And we'll show you how we use our machine vision FCNN and also a genetic algorithm to do that for us so that we don't have to worry about calibration at all. So we're coming up with an open source package for this, so we can release it, and it can be a nice alternative to PIV in the future. So you might be thinking, oh, why can't we use other software? Well, our program is called FCNN segmentation. We compare it with other thresholding techniques. At the top is a slurry flow, a wet one, on the top left, and on the top right, we have our detected flow using FCNN segmentation. It's not bad. If you look at other thresholding techniques at the bottom, you can see that it cannot distinguish between the tree stems and the flow, or there are huge gaps inside the flow for other thresholding techniques. PIV can only give you velocity fields if you have tracer particles or if you can detect the texture in the flow. And you'll get lots of PIV vectors that are not easy to use for calibrating because you have so many wild vectors. So this is the advantage of our FCNN segmentation technique for complex flow structure interaction problems. So what are we doing? Well, we're creating physical experiments. On the left, we use our FCNN machine vision algorithm. And on the right, we have a digital twin of our experiments. This is an overlay. Now, what's the problem? The problem is the digital twin has no constitutive behavior. It has no physical behavior, no rheological constitutive behavior. It's just a digital overlay of the experiments. So what do we need to do? Well, to use this so-called digital twin, we need to give it mechanical properties. How do we do that? Well, we can use constitutive models that are well established. In this case, I work with my collaborator, Dr. Jin-Hung Chu, who's at KAIST now, to use a material point method simulator to model the transition from elastic to plastic behavior. We use the Drucker-Pracker criteria. We use a mu-I rheology for the granular flow. And we also can capture the effects of gasification. If you remember, I mentioned that sand can be either solid, liquid, or gas. So we can model all three phases of the granular behavior. And on the left is just a typical plan and side view of a collapse of the sand on our tree board without trees. So any MPM model, numerical model, is only as good as the input parameters that you give it. We always hear garbage in, garbage out. It's true. And it can be even more tricky when some people are trying to publish papers and they only show you one calibrated case. If they do 100 tests, they only show you the best match case for those 2 tests. But how do you prove that your input parameters work for the 100 different cases, right? Well, this is where we have to borrow an approach from nature. And we use a genetic algorithm. This, of course, has nothing to do with my research, but it's just a simple concept of evolution. We have a new generation of turtles here. You see 2 turtles, one with a shell, one without a shell. We probably guess the shell is good for protection, so the one without the shell is not going to make it. And then the ones with shell continue to reproduce, and hopefully they mutate and they turn into a larger turtle with a brown shell. So what's happening here? We're taking the best attributes for each iteration and we mutate it until we get the best version of our input parameters. So we carry out automated calibration of our MPM model just by using intersection of union, which I'll talk about in the next slide. So what are we doing? Well, we input an initial guess for the input parameters. This initial guess must be within the physical constraints of a parameter, right? We're not going to put a friction angle of 100 in, right? For dry sand, we're probably anywhere from 25 to maybe 40 or something as a maximum bound. So we input the physical extents and we let the genetic algorithm compare all 100 of our experimental cases and come up with the optimum set of input parameters to run. So we carry out iterations, we find the best parameters, we mutate them and preserve them. How do we know whether a set of parameters is good or not, you might be asking. So that's where IOU comes in, maximizing intersection of union. What is the key performance index? Well, I just mentioned we use intersection of union. So we take our digital overlay, our digital twin, we compare it with the experimental results,
we overlap it, and we see how different it is. If it matches perfectly, we have an intersection of union of unity. If it doesn't, it's 0. And we just try to maximize the intersection of union for a wide range of experiments. And then we get a high fidelity set of input parameters. So how did our genetic algorithm work? Well, what you see here are two cases. On the left, we have 20 degrees. On the right, we have 24 degrees for the slope. The red line is the physical experiment, digital overlay from the FCNN. The blue blob is the MPM. So it works quite well for a different range of inclinations. So what happens if we put in the forest? So this is the same input parameter, right? We haven't changed the input parameters for different simulations. It's the same set. Well, for trees, it gets a bit wacky at the front. I would still say it's acceptable, right? The red is the experimental digital overlay, the blue is the experiments. And then if you have a denser configuration, we're still doing well. We're not picking and choosing, right? We're uploading these entire videos for the reviewer to look at during the review process. We're not just showing a few snapshots and say, look, we have a great match. For any manuscript now, we can actually provide the entire video to show that we have a high fidelity set of input parameters for a wide range of simulations. And this in the past has been very time consuming to do for any researcher working on dynamic landslide problems. So we can use our model now to carry out near real-time back analysis. We can look at different patterns. Here's a rectangular pattern or square pattern. An interesting phenomena, though we just started the research, is the trees, although they're not channels, they behave like channels. So if you have a rectangular pattern or square pattern, you can accelerate the flow through momentum concentration in the middle and increase the travel distance or mobility of a flow. If you densify the forest, you still get the same phenomena, but it becomes a lot more dissipative in nature. The flow front travels quite far, but the density of the flow front is not as significant. So this is what happens for a square regular pattern. What happens if we use staggered formation? Well, it becomes very effective at acting as a natural barrier to kill all momentum. So what happens if we make it more sparse? Well, you still see the channelization effect if you zoom in. So it's a scaling issue. It depends on how you scale your forest relative to the flow parameters is what we've noticed. So in between tree stems, we see something we call momentum boost, which makes the flow move faster, travel further. And you can also have momentum dissipation when the flow hits an adjacent stem downstream. So there are competing effects between momentum boost and momentum dissipation. So if we have the concept that by putting a forest along a slope must be better than not putting a forest, this may not always be the case because you can have momentum boosts depending on the ray configuration of your trees. You might be thinking, who actually grows trees in a square pattern? Well, for cultivated forests, it's very normal. We use square patterns. Evidently, this is not for a debris flow, but there are square and rectangular patterns for cultivation because it's easier. If we want to use cultivated forests as a natural barrier against landslides, we need to visit the spacing and pattern that we adopt is what we want to say for a potential implication at the very early stage of our research. So some key conclusions for the nature-based solution. Most of the geophysical flows that we deal with tend to be supersonic. So we have to be able to capture the bow shocks that form. Bow shock interaction can either boost momentum or dissipate it. The momentum boost can increase the travel distance and velocity of a flow locally. And we tend to want to use staggered formation for cultivated forests, which might be quite obvious, but it's not so obvious if you realize that there's still momentum boosts going on locally. So I've been talking for a long time. My throat's getting dry, but the last part is defining new frontiers. So this part is just me as a researcher trying to motivate young geotechnical engineers to pursue a research career. Why I want to do that is we need more scientists to tackle pressing issues in the world. And there are a lot of pressing issues in terms of geotechnics. Climate change will cause a lot of problems for us. We're going to see extreme rainfall events that cyclically, with drying and wetting, can affect the movement of slopes. What you see at the top left is the Big Sur landslide along California Highway. And this landslide has been moving slowly for years. And the question that has caused a lot of problem for engineers is, when will this landslide accelerate and run out? How do we understand the effects of climate loading on this landslide? And this is not a slope instability problem because there's already a well-defined slope surface here, right? It's just moving, it's sliding frictionally on here. When does it accelerate? When does it decelerate? When does its strength harden? When does its strength weaken, right? So these are complex climate change related issues. There are lots of slow moving landslides around the world. Another problem is we've seen a substantial increase in wildfires globally over recent decades, and some of these have been devastating for ecosystems. We know that forest fires will alter the properties of soil. It'll make the soil hydrophobic. Hydrophobicity causes water from the rain not to be able to infiltrate and run off instead. When it runoffs, it erodes all the surface material and you can generate debris flows very easily. So do we really understand the trigger mechanisms and thresholds for wildfire debris flows that have a very substantial hydrophobic component in it? How does this ecosystem get affected by plants that are burnt and only the roots are inside the ground? But the roots are also interesting if you think about it. By burning this plant, the roots have probably shrunk a bit and it's even stiffer than before. Does that increase the mechanical reinforcement in the ground? Does that minimize the effects of erosion by debris flow? So there's lots of interesting questions pertaining to wildfires. Last but not least, of course, we have thawing of permafrost regions around the world. So climate-driven landslide dynamics will be a very interesting topic for researchers to tackle moving forward. Other types of landslide-related problems, we've also been looking at submarine mass movements. Why do we care? Well, we're moving offshore. We're building infrastructure offshore. And these submarine debris flows do pose a threat to our infrastructure. They impact it. They transport mass amounts of sediment. So off the coast of Africa, one of the largest landslides ever recorded went on for days under the sea, and no one knew that was going on, right? So these landslides are not just affecting infrastructure, they're transporting pollutants further out in the sea. One question is microplastics. We see that there is an increasing microplastic concentration in the seafood we eat, in the fish we eat, in the shrimp and prawns that we eat. We're detecting pieces of plastic inside the food that we eat, right? So how is it getting there? Well, coastal cities, when we discharge our effluent from something simple like washing laundry from a machine, plastic fibers will also discharge. We have all sorts of plastic from tires washing out into the sea. And there's actually a lot of plastic around the coastal regions of our cities. And these submarine mass movements doesn't necessarily have to be a debris flow, it can be any type of gravity flow, is principal in transporting these microplastics out. So as a public policy issue, do we need to think about the plastic footprint of coastal cities, right? Not just carbon footprint anymore. We're causing problems with our food chain now. Shrimps are eating this plastic at the bottom of the sea. Do we need to tell policymakers that, yeah, maybe we shouldn't allow polyester or some type of fabric to be washed or to sell these type of fabrics because they create plastic fibers? Do we have to continue to minimize plastic pollution? How do these plastics get transported? How do they get buried? Do they get reactivated? So this is an interesting problem related to submarine landslides, which are an entirely different animal. So this is perhaps an interesting area to look into. Last but not least, I think it's interesting, more blue skies, to look at the dynamics of landslides under hyper and microgravity. Varun, Om, and I would know that hyper is just a fancy word for centrifuge modeling, and micro is gravity less than that of Earth, 1G. How do we simulate that, right? Is the only way to go on a jet and to simulate microgravity conditions for a few seconds? Or is there a smarter way to simulate microgravity? And we can study how flow-type landslides move under hypro and microgravity. So I think these are very interesting research directions to push the forefront of knowledge. So I promised 1 hour and a half. My voice is getting raspy. This is all I want to share with you today, Professor Kemchun. So if you have any questions, feel free to contact me using any of these means. Yeah, thank you again.
All right. So thank you so much, Dr. Clarence. I think your presentation is one of the best that I have ever heard of. So yeah, it really kept me concentrated to your presentation. Is actually I wanted to work on the other paper, but when I listen to your presentation, I cannot stop.
Thank you. Thank you.
Listening to that. It's very interesting. Actually, I wanted to listen to your early part about flexible barrier, and then I was caught up by the second part about those kind of nature-based solution. Is very interesting and paving up the new way of research, especially you integrate all those AI into your research, and also you have a digital twin, which is also another new branch of research that is very popular right now. And at the end, actually, I think you already motivate some of the students here as well. So I really need to say thank you so much. And I think if you don't mind, we may try to open up the floor for some questions. Maybe you can drink some water for the time being.
Yeah, I'm okay. I'm okay. We can open the floor up. Yeah, I'm
All
okay.
right.
Thank you for your offer, Dr.
Yeah. Any question from the floor? Any student, any attendants would like to ask some question? I see Dr. Tayanan also here. So
Yes, yes. Nice photograph. I'd rather see his real face though. Yeah.
Yeah, I'm not sure he's here or not, and we can see his display.
Yes.
So anyway, any question?
I have questions.
Yeah, please, Awan.
Okay. First of all, I would like to thank you to Dr. Choi for the interesting presentation. Allow me to ask 2 questions, Dr. Choi. First, I think it's very basic question. What is the condition? I mean, kind of soil properties or water content or maybe rainfall intensity that can induce debris flow in natural hill. And my second question is, we need to investigate the condition of boulder. I mean, the amount of the boulder or dimension of the boulder in slope in advance before designing process, before we design a barrier in our engineering field. I think that's my question. Thank you, Mr. Chair.
Okay, I'm just going to recap your 2 questions. The first question is, what are the factors that trigger debris flow, right? And the second question is, can we do some advanced work to survey these boulders beforehand, right? Okay, thank you for your question. The first question is, I have a really bad memory. What was the first question? The first question was, how did debris flows initiate? It's actually quite interesting that you asked this, because from my point of view, I wouldn't say it's well researched, because not too many people have actually seen a debris flow initiate, right? We can guess that there are a few mechanisms. One is you have very high stream loads in the gully. So there's lots of rain, you have very high velocity water eroding the beds of a channel and the banks of a channel, and the solid soil concentration progressively increases. And that's a progressive generation of a debris flow. There's also instances where you have lots of soil blocking a river and water impounds it, and then it bursts like a dam break situation. There's also cases where you have a slope, slip, fall onto a bed of soil, liquefy it, and the entire mass liquefies and turns into debris flow. But your question is interesting to me because how many people have seen this in the field, right? They postulated mechanisms. So this might be another area worth researching, if you ask me, because normally we don't look at this problem in a lot of detail because we don't have a lot of evidence. So that's the first answer to your question, not so comprehensive, but I hope that helps a little bit. The second part is about the boulders. I'm not sure about the geotechnical engineering practice around the world, but in Hong Kong, we do boulder surveys. Before we do any mitigation control, we count the number of boulders, we measure the size of the boulders, and we're able to estimate how many boulders we have to design for, what their size is beforehand. You're absolutely right about that. So I hope that answers your questions, Arwan.
Okay, thank you. Thank you, Dr. Choi.
I think there's more people want to ask the question.
Ajahn, I have a question.
Yeah, please.
Okay. First, I want to thank for the opportunity to listen about the very interesting from the Dr. Choi. I have one question related with the forest that you said before, that the tree can also reduce the debris flow. Do you think since the in the forest not only the tree exists but also like the small with grass, so should we consider it that can I mean like the roughness of the surface can reduce the speed of the debris flow, right? So should we consider like the small grass that live on the surface on the at the forest? Thank you.
Okay, yeah, thank you for your question. So your question is asking whether we should consider smaller vegetation at the boundary and perhaps the different types of surfaces, including rock surfaces and other types of terrain. My answer would be yes. If we want to progress towards realistic simulations of how far a landslide would travel, we should consider those. I've always been struggling to decide whether I want to study the effects of vegetated surfaces on the movement of a debris flow. I'm just not sure I've convinced myself that this may be a major factor, but I haven't been unconvinced that it's not a major factor. So you're right, it's an interesting direction to look at. I've thought about it, but I haven't been brave enough to put a PhD student on it yet because I'm worried that it may not be so significant. So it's a good question. Yeah.
Thank you.
Right. So I think that's quite a good question and also trigger a further question for me. I think it's one of my questions also related to Urena question. I think I saw that you use kind of the stem of the tree to kind of differentiate the cone as you predicted in numerical modeling. So I think it's related to the stiffness. Let's say that some glass is already really tall as well, but they don't have the stem. It's just only the leaf. And perhaps it's more likely toward the flexible barrier rather than the rigid barrier. So that's why I'm thinking like, do you think any criteria between that? It will be very useful to determine whether the glass will be helpful or not. I think if we can find that kind of criteria to justify that, okay, this glass is kind of contribute enough and that should be okay. But I'm not sure that will be a good or useful research way to do that. I mean, in your opinion, because you are expert on this field already.
I think that's a really good idea. In fact, I probably want my PhD student on this topic to look at the bending stiffness of these stems. Like you said, it could represent a wide range of vegetation from something smaller to something very stiff. I think it's very interesting, Varun, that you mentioned that it could change the shape of the cone as well, right?
Yeah.
And it could change the overall forest scale dynamics, not just stem scale. So I think you gave an excellent suggestion, and I'm definitely going to tell my PhD student to look into this.
Okay, I'm not sure if it's a suggestion or not. Maybe
No, I think it's a good idea. It's a really good idea. Yeah.
because I'm also kind of interested into that kind of research, but it's just like root uptake. More likely not like a derivative flow, but it's just like lateral resistance from the tree. So yeah. Before we going for that, any more questions from the floor? I think
I
that's a
have
good
one question,
Yeah, please.
and more of an academic aspect. I'm interested in applying all the way till doctrine, and I kind of want to know an insight of what should be prepared or what would be a best way of tackling or getting into a PhD degree. Any
Okay.
advice?
Right. Sorry, are you referring to PhD in general or PhD in Hong Kong, or
Both would be great as well.
okay, your question, sorry, I just want to summarize. The question is how to prepare for carrying out a PhD, right? Is that right? Am I
Yep,
correct?
like for example, you specialize in the one that you presented, the landslide things, right?
Mhm.
For example, if I were to study into those field, what would be the course to prepare? Do I have to take like a certain amount of experience in working in a job, or do I just prepare some files from after graduating a graduate degree and apply immediately?
Yeah, that's a good question. I think maybe Varun and I can partially answer this both. I think this is subjective though, because for me, I don't know how Varun feels about this. For me, I feel I have a lot of bright students that come directly out of bachelor degree, and they haven't been brainwashed yet with some other research program. And Varun and I feel, I think from our supervisor, that if you're a strong researcher, you don't really need courses. You can learn on your own. But to be good in the landslide field, you need to have strong soil mechanics. If you want to look at flow-type landslide, you should be strong in fluid mechanics. But other than that, I don't think there's anything to prepare for research. You just have to have a very good attitude, want to do it, be genuinely interested. That's the most important thing for me. Yeah, I don't know. How do you feel, Varun?
Yeah. I think that is kind of anyway. I think if we would do the job, it depends on the individual person as well. I know he is from undergraduate student, so I mean after he graduated, so maybe you need to continue for the job or master degree or even PhD. But I think first of all, Dr. Choi is right. So you need to be very strong for your academics, so that you can be very good at the job and both continuing study as well. So we cannot avoid that, of course. And you should listen to my class. And next thing, of course, you need to choose which future you would like to go. And Dr. Choi already pointed out a lot of problem really nicely. What will be the future problem in your generation? Because you cannot think about the problem now. After this, where I think after 10 years, it will be your time to be a senior engineers or after PhD work. So you need to think about the future problem, not the problem right now, right? So you need to lay out your career path, which way you would like to go. And if you are really interested in this kind of landslide, Dr. Choi already pointed out about those climate change, about the plant, and about those things, plastic issues that can be the problem in your generation, not our generation anymore. We are quite different now. So I think the most important thing is to target your objectives nicely, right? So, and then you can go ahead. If you go for the job, it works fine, right? So that is my opinion. It's subjective, of course, as Dr. Choi said. Yeah. Right, but it's good opportunity as well because Dr. Choi also one of the professor that have a lot of students in Hong Kong, and actually Rachata also one of the good student in my class as well. So I mean, if you would like to continue master degree or something like that, I can recommend you, no problem. So but yeah, it's up to you, up your skill, whether Dr. Choi is likely to agree with me or not. It doesn't matter later. Okay.
Yeah, yeah, if you're interested, like Professor Kamchun says, let me know. We're always looking for bright candidates to join our team. Yep.
So yeah, thank you. And any more question from the floor? I think we got quite a lot of people. Usually they don't ask the question. So that means your presentation is so good.
Thank you, Varun.
No more. If not, I may, if you don't mind, maybe just a few questions from myself as
Okay,
well.
yeah, sure.
Yeah, why you need to? No, my question is very simple.
Oh.
Very simple, man. Actually, I was wondering in more practical point of view. You said that for your, like, let's say, for example, like the boulder problem, you have the mitigation approach. Let's say you put like a steel pile into the ground, as simple as that, and then it can obstruct the big boulder, right, and stop the boulder like there, or decrease the impact energy, slow down them. That part is okay, but I'm thinking of course, the debris fall not happen just one, maybe after they happen and the structure already be destroyed. So I would like to ask a further question is, in the practical point of view, how can we clear up all the work? Or we need to repair that, or we need to build that again? And if so, actually the soil surrounding that is already weakened by the damage. So we need improvement or not? It will be cost more or not? So that kind of thing, I'm not sure in the practical point of view. So
It's a very good question, Varun. You know the second design I showed where we dug a hole and we just put a steel member in? One of the reasons why we did that is because, well, at least in Hong Kong, after each event, we're supposed to replace all the baffles again. So we want it to be cheap. And also we want the steel members to be so we want some workers to be able to carry that up, right? Up a slope, steep slope. But then you asked a very interesting question. If the soil is eroded all the way to the rock, what do you do? I guess you have to put the baffle somewhere else where there's competent soil to build a footing, or maybe there's another way to install the baffle into rock, I guess. Not sure how that would work, but it's a very good question. Never thought about that. Yeah.
So in terms of like in practice, maybe it's better to find a new location, and
perhaps
rather than repairing at that location, right? I'm not too
You're
sure. So it's like a way forward, because I'm quite like interested in your work that aiming for the practical work. And
you're right about that. Yeah, I noticed the erosion is very significant. Often the soil's eroded all the way to the rock bed and there's no more soil. So then I think you're right. Maybe we have to look for a new location. Yeah.
It's just a random question, maybe, but it will be kind of one point that because I'm also working for kind of consulting work as well, and we got quite a lot of problem in practical that my research actually cannot really directly apply to that. It's a lot more some kind of troublesome out there. So maybe you experience that. For example, your presentation, you said about those kind of rigid barrier. We need to dig up all the mass that going down, and they are not supposed to design for a permanent condition to receive all the weight. That one is just triggering me as well. So I just know that I didn't realize that. So yeah, so some kind of this, if you involve more into the consulting work, is also strengthening your research to be more practical as well. So really impressive. So yeah.
Thank you, Varun.
And yeah, that's it for me after listening to your presentation. Any more question from people here? So if not, I think we have quite a really, enough time. We have like 1 hour and a half from a great presentation from Professor Clarence, and we have some good questions from the floor as well. So I think I would like to end the presentation and seminars today. I would like to really thank you for a great presentation from Professor Clarence, and hopefully if we have a chance, maybe soon later in the future, we would like to welcome you back here again to give us the presentation, or even on-site presentation. It will be perfect. So yeah, today I would like to say thank you for you, Dr. Choi.
Thank you.
Thank you so much.
Thank you. Take care then, Varun. I'll be in touch
Okay.
with you soon. Yep.
Thank you, everyone. So,
Thank you very much, teacher.
Thank you. Bye.
Thank you.